So, we've looked a lot at various aspects of the file system. Now, we'll go very specifically and look at some notions of the xv6 file system and how it is implemented. So, at a high level, the xv6 file system has multiple layers. So, we have the file system interface right at the top. So, this is where this is the layer which would essentially receive the system calls like open and write and read, for instance. Right. So, this is the layer which essentially collects these system calls and is first to essentially implement them using functions such as sysopen, syswrite and sysread. Of course, there are many other system calls as well, like close, fseek and things like that, but we are just limiting to the very basic system calls of open, write and read. Now, once so the second layer is essentially where we identify the device which is going to handle these system calls, whether it's an hard disk, whether it is any other device, and we also resolve path names for specifying a certain to identify the file in a certain path in the file system. We identify also the inodes and the directory. Right. So, one thing to actually note over here is that the typical way Linux works is that even devices are essentially can be accessed like a file. So, for instance, in Linux, I could essentially use the open system call and specify something like this /dev /tty s0, for instance, and I can open it for, say, writing. And this would essentially open the serial port, the UART serial port, and any reads or writes to this particular file descriptor would essentially be directed to the serial port instead of the hard disk. Similarly, similar interfaces, as we have seen when we spoke about the IPC, the inter-process communication, we could essentially use the same kind of open system call for instance for pipes or to open sockets and things like that. Now, all of this is essentially resolved in the second layer. So, at this particular layer, with the help of some specific numbering of the devices called the major and minor numbering, the device or the target device would be essentially resolved. So, the OS would determine whether this particular data which has been written or the data which has been read should essentially be targeted to, say, a particular peripheral like the UART or say the USB or for instance the hard disk, right. The third layer is essentially the log. So, we have discussed the log and how to ensure the log can be used for journaling. Then there is a buffer cache, and finally there is the IDE, right. So, the buffer cache is essentially present in the memory, and it is used to cache blocks present that are essentially stored in the RAM. Now, the reason for essentially caching these blocks is that the access to the DRAM in a system, it's much more faster than the access to the hard disk, and therefore buffering these blocks in the DRAM would essentially have tremendous performance benefits. The final block is essentially the IDE. So, I'd like to actually note over here that the older versions of xv6 use the IDE, but the new versions, in fact the versions that we are actually looking at right now, is essentially using the virt.io, right. Or so the virt.io and the IDE are essentially the device drivers for the hard disk, right. So, these low level things would essentially communicate with the hard disk using the memory mapped IO registers. Of the hard disk to essentially initialize to initialize the disk to essentially convert the address or rather, so the word so the lowest level, the word IO and ID are essentially the device drivers, which uses the memory mapped IO registers present in the peripheral, in this case the virtual IO hard disk or the IDE hard disk, to essentially communicate and with the hard disk, to essentially set up interrupts, uh, to ensure the transfer of blocks of data from the hard disk into the main memory, and so on. Also, what it essentially does is it converts the addressing, which is typically in a linear address, to an address which the hard disk can essentially understand. So, in the IDE, as we've seen before, the addresses are essentially correspond to the sector number, the head, and the cylinder number. In the VirtIO, it is far more simpler. The linear address is just converted to a sector number, right? So we'll look at many of these blocks in more detail. So one thing we're going to start off with is the important data structures. So we look at the data structures that are more applicable to the top level. So this would involve the file data structure and the inode data structure. So the file data structure essentially would corresponds to each file. So every time you create a file, you would essentially have a pointer to one structure of this particular form, and notice that it has an entry called the type. So the type could be either a pipe, it could be an inode or a device, right? The reason for this is that, as we've discussed, the same system calls of open, read, and write could be essentially used for peripheral devices or for inter-process communication like a pipe, or to essentially read or write data to the hard disk. Now, in the latter case, where you want to essentially create a file in the hard disk or read or write to the file in the hard disk, the type is essentially FT inode, right? So here we have a reference count. So recollect that in previous videos, we've essentially had one reference which counted the number of times a particular file was opened. So this was a global structure which every time a file was essentially opened, there would this particular counter would be incremented. So this reference count is actually present and defined over here. So then we have this readable and writable, which essentially maintains whether the file can be read or written to. And yeah, so we have aspects of for the pipe over here. So very specifically, if the type is a pipe, that is for an inter-process communication, then this structured pipe and the pointer to the pipe would be present here. On the other hand, if this file corresponds to a file that is stored in the hard disk, which is of type FT inode, then this particular inode structure is essentially utilized, right? And other important thing is this aspect of the major number, right? So this major number is what essentially distinguishes a file. This major number is what essentially distinguishes a device like a peripheral UART and so on from something which is essentially stored in, say, the hard disk, right? So if you have say multiple hard disks present in your system, say you have a master hard disk, a secondary hard disk, and so on, each of them would have a different major number, right? So what this would essentially indicate is that you could use this major number to first identify which device you want this operation to be targeted to, or where you want to essentially read or write this particular file, and then go into that particular device and address the various sectors or the cylinders and so on that are present, right? In a similar way, in xv6, we are restricted to just 3 devices, the hard disk, the only device that is present is the UART, and of course we can have multiple pipes as well. So one thing which is important over here is that the structure inode, right? So so the struct file has a pointer to the inode structure, which is essentially defined over here. So this structure is essentially the in-memory copy of the inode. So we have two definitions or two definitions of inode. One is the inode corresponding when a particular file or block is stored in memory, and the other one known as D inode, which we will see later, is the inode contents when stored in the disk. So what you'll see now is that there are a few entries which are essentially different. So the device here corresponds to the device number. The inode here corresponds to the inode number for this particular file, and the reference count again present here is very similar to that present in the file. Here we have a valid, which essentially means that whether the inode has been read from the disk or not. So we have other things such as the major, minor, and so on, right? So important over here are the addresses. So these are the addresses corresponding to the hard disk, corresponding to where in the hard disk this particular file is stored. Okay, so we go now to one step lower, and we essentially look at what the file system structure in for xv6 is. So at a very abstract level, the file system can be considered as a contiguous set of bytes. So each and as we have discussed, the smallest addressable byte is a block which is of 512 bytes. So we have multiple blocks starting from 0, 1, 2 and so on, each potentially holding data corresponding to metadata for this particular file system, or data corresponding to various files. So the block number 0 is the boot block. So this is where potentially where you could essentially start executing. You could have a bootloader present at this particular block to essentially start off the operating system, or start off the to essentially start off booting the system. Now the second block over here is the super block, a super block which comprises of contains these 4 entries. It has the size of this file system in terms of number of blocks. It has the number of data blocks present, the number of inodes that are present, and the number of log blocks that are present. So for instance, we have this is our inode array. This is the number of data blocks, and this is the log blocks that are present, right? Within the inode array, each entry has this particular structure known as D inode. So as we have discussed earlier, this D inode corresponds to the disk inode. So this is the inode present stored in the disk. So it has a subset of the elements that's present in the struct inode. It has the type, the file type. It has the major and minor number, which is corresponds to the device, the specific hard disk. It has the number of links to the inode in file system, and importantly, it has addresses for the data block addresses. So corresponding to a D inode, it essentially has pointers to these data blocks where the file is essentially stored.